This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics, Learning Objective 2.3.2, looking at the dependent motion associated with pulleys. This is a subset of relative motion covered in Chapter 11.2c of your Beer and Johnson textbook. And in this section, we're going to look at a subset of relative motion. In our last lecture, we learned about how we can relate the motion between two bodies. Now we're talking about looking at particles where that motion is actually dependent upon a relationship between the two. So when we think of dependent motion within particle kinematics, we're looking at motion where it's dependent, hence dependent motion, on one or more other points. So dependent motion dependent on one or more other points. Examples of this would be pulleys, which is what we'll talk about today, gears, wheels, which we'll talk about when we get to rigid body kinematics, cogs, all sorts of things like that. So any place where we have contact or some sort of interaction that causes that dependent motion to be connected. So if we look at a system like this, so we got a system of pulleys here. This is what it might look like in the real world. I've actually got this system of pulleys set up here on the board. And so this is point A, where this block is, and it's attached to a pulley. And then up here is point B, which is actually another pulley, but it's fixed. And then finally we have point C here. And so when we think about the dependent motion, the idea is that if I move C, A is going to move. And there's going to be some relationship between those two. So when we think about pulleys as a system, it's all built on the idea that the length of a rope in a pulley system is a constant. Okay, so if you look at your book, the chapter on pulleys basically says, okay, if the rope's length is constant, then we can say that if we set up a datum, an origin point, say where all the fixed points are, that if we look at the length to where each point is and we add that up, that total length is going to be constant. And so another way we can express that is using this equation where we would say the sum of the number of ropes at each moving point times the distance at each moving point is equal to a constant. And that constant is roughly equal to the length of the rope plus or minus the little bits that curl around the pulleys. So this is the base equation. So if we take the derivative of this with respect to time, we would see that the number of ropes stays constant, so that pulls out in the derivative. The derivative of position with respect to time is velocity, right? And then if we take the derivative of a constant, it's going to be equal to 0. So it would look something like this. And if we take the derivative a second time, we're going to get acceleration. Now, the other thing to recognize is that this constant means that for any given point, this sum of the n time SI is going to be the same. So if we were to set them equal to each other and do the difference between the positions, we would also see that's equal to 0. So sum delta S for each individual point is equal to 0. And it turns out that these are our dependent motion equations for pulleys. Now, there's a procedure to this, which I'm going to put right over here. And our procedure to doing this means that we have to follow a particular sign convention. Now, this is something that your book doesn't do a great job of. In fact, I haven't seen a book that does a super great job of this. So my hope is that the process that I explained to you here in this video will help you through that. So I'm going to increase the size of the video a little bit so that we can make sure we can see this clearly. So we've got these equations. And the first thing we want to do is we want to establish our sign convention. So in this case, we need a local sign convention. Okay, and so for each moving point, we want positive to pull away from the fixed point. All right, It's critical that we say pull, because later we're going to learn about pushing ropes that would create negative sign convention. Okay, positive pulls away from the closest fixed point. So if we look over here at this pulley system, we've actually only got 2 moving points, and at each location we can draw a new local datum like so. And then if we look at where the closest fixed points are for A, well, they're up here. And so away from those fixed points is going to be down. So this is actually going to be positive down delta S sub A. Likewise, if I look at point C, the closest fixed point is up here. And so it's going to have to point down for my positive sign convention. Delta SC, like so. All right, so we see that we've got our local sign convention. Our next step is going to be to count our ropes as they're attached to each point. So if you think of it here, we're establishing our delta S, and here we're going to look at the number of ropes. Now again, here we're going to have a positive and negative sign convention. So positive is when positive movement pulls the rope. And negative is when positive movement pushes the rope. Now, some of you might say, pushing ropes, it's a terrible plan. I agree. That's why it's negative. All right, so if we look over here at this system, and we say, okay, well, if I pull on this pulley here, right, I'm going to pull on how many ropes? Well, I'm going to pull on 1, 2 ropes. So in this case, my NA is equal to 2, and it's a positive 2 because it's pulling. Now I'll show you a situation here in a minute where when we pull on it, we'll actually push some ropes, generating a negative NI. Over here, same thing, okay? So if I pull in the positive direction, move it or create positive motion, it's pulling the rope, and there's just 1 over here. So NC is equal to 1. So we count our ropes. So these things you have to do by point. And then once you've done that, you can use your rope counts as coefficients, and you can write your dependent motion equations for each rope. Okay, so if I were to come over here, I've got 1 rope, 1 continuous piece of rope. So I'm going to have 1 set of equations, and these are my dependent motion equations. Now this one that's set to constant, I don't think it's all that helpful. So typically I'm just going to stick to these 3. I might rearrange them. So if I start with the change in position first, I'm going to notice that 2 delta SA plus 1 delta SC is equal to 0. So that's this equation here, dependent motion equation, written right here. So the idea is that if I pull in the positive direction on delta SC, that I'm going to get a negative motion of half that delta SA, so that when you add this all together, you get 0. Hopefully that equation makes sense to you. Okay, and then we can just repeat the process for velocity and acceleration. So 2 velocity at A plus the velocity at C equal to 0, and 2 acceleration at A plus the acceleration at C is equal to 0. Now, real quick point, when we count our ropes, when we do our local sign convention, we're doing this by moving points. So we're ignoring B because this point doesn't move, right? There's no motion there. Its velocity and acceleration is always going to be equal to 0. So now I've got these three equations, and if I were working a problem, maybe I would know about the motion of one of the points and be looking for the motion of another. And in fact, this brings us to degrees of freedom. So how many points do I have to know where it is to know where the other object is? You can read your book on that. Don't really worry about being able to calculate degrees of freedom yet. You'll get to it in a structural analysis class. But this is the idea here, is that I can then, let's say I knew everything about where C was, I could use this dependent motion set of equations for pulleys to figure out everything about A. So hopefully that's clear. Let's look at another situation that we might encounter that's a little bit more complicated. Okay, let's look at this situation. Now again, we could set up all of those various points here. Now what's special about this is that there's actually two different ropes. So let me change my pulley configuration here, because what's going to happen is that, again, we're not terribly worried about that point B. Okay, like so, and got a guy there. Okay, so point A and point C are the same, but now I've added a whole new rope. Do we see this? Okay, and let's see if I can do this well. So what I need to do now is figure out for this second rope. So for the first rope, the equations are all exactly the same. We've actually done the work. But if we wanted to look at the second rope, I'm now going to have some different things going on. So I've already got delta C set up here where this pulley is, right? Formerly it was just a block, now it's a pulley. The trick with this is that there are now 3 degrees of freedom, so I have to keep track of 2 things first. Okay, I'm going to pull this off so that it'll actually stay. Okay, so over here at C, now I've got a situation that when I move point C in the positive direction, I'm going to be pushing ropes. So I've already set up my, let's start at the top. Local sign convention. Delta C is good. See, we call this point D over here. Delta SD. And then where the pulley is, that's delta SE. And in each case, the closest fixed position is still up here at the top, so my positives is still down. This is going to be useful on one of your homework problems where there's a weightlifter pulling sideways, right? And so there's a fixed point away from them on the weight machine, and then positive is away from that, so away from the closest fixed point. Now we can count the ropes, and so if I look at delta SD, if I pull down, I'm in fact pulling one rope, and so that's going to tell me that N at D is equal to 1. Okay, and if I look over at E, same thing. If I pull down on this pulley, I'm pulling on 2 ropes, 1, 2, and so N at E is equal to 2. Now the trick with point C is that when I move this in the positive direction, so I move down, I'm actually going to end up pushing the 2 ropes on this one rope that I'm looking at here. So for this second rope, NC is actually equal to -2. Okay, so I've done all that, and so now I can write another set of equations for this second rope, and that's going to tell me that I'm going to have delta S sub D plus 2 delta S sub E minus 2, I'm going to give myself a little bit more space, delta S sub C, because we're pushing those ropes, all equal to 0. So now there's more things going on there, and then I can do the velocity and the acceleration. Like so. And so now for this system, I have 6 dependent motion equations. And if I can figure out if I know what's happening with these other systems, then I can go through and do that. So that's our pulley procedure. And I look forward to working a problem with you in class. Thank you.